Okay, great. I am incredibly pleased to introduce Bryan Terrazas. Bryan did his PhD at University of Michigan, and then he is now a Future Faculty Leaders Fellow, which is a real mouthful, at Harvard. The Future Faculty Leaders Fellowship is aimed at supporting people who are leaders in both astrophysics and social justice, and Bryan is indubitably a leader in both of these things. Bryan does work on one of the most pressing problems in the study of galaxy formation and evolution, namely how black holes influence the formation and evolution of galaxies. This is a really hard problem, which is why most of the rest of us have just thrown up our hands. But Bryan is an expert in both theory, observations, and synthesizing the two of them to place novel constraints on how black holes influence the growth of galaxies. I'm really excited to hear his talk today. So everyone, please welcome Bryan Terrazas.
Thanks so much. Thanks so much. It's great to be here. Can everyone hear me? Zoom too. I hope it's all good. So feel free to stop me in case something breaks on Zoom or something. Yeah. So I'll be sharing some of the work that I'm doing on trying to understand how black holes shape galaxy growth and galaxy evolution. And I hope that by the end of this talk, you'll be able to understand a little bit of how I see black holes fitting into this picture of the beautiful diversity of galaxies that we have at Redshift 0 today. So just to give a little bit of a structure to the talk, first I'm going to give you an introduction to the way that I think about galaxies, black holes, and the star formation that happens in them. And then I'm going to go into some of my previous work on looking at how black hole mass and galaxy properties link up, and how that can give us information about the physics of how black holes affect galaxies. And then I'm going to talk a little bit about my current work that looks at observing a simulated galaxy with a black hole wind in the center. And then I'll just give you a little bit of a summary and takeaways. So my intro first. So we live in the Milky Way. We're here on Earth, and we can see that the Milky Way is our home galaxy that is a disk that spans the sky this way. And so if we were able to zoom out, then we'd be able to see that our galaxy is made up of stars, gas, dust, the supermassive black hole at our center, and dark matter, which is not pictured here. And then if you were to zoom out even farther, then you'd be able to see that we're not alone, right? We have other satellite galaxies around us that are embedded within our own dark matter halo. And then we also have a companion Andromeda that has its own satellites as well that are embedded within its own halo that are gravitationally bound. And what's really cool is as you zoom out further and further from the Earth out into the local universe, you can start to build a picture of what the large-scale galaxies, how galaxies are distributed around the local universe. And so you can take data this is from the Sloan Digital Sky Survey, and take the position on the sky and also the redshifts and start to make this large-scale structure visible to us and be able to understand what the data is telling us. And what's cool, so here is the Earth. And we basically, SDSS looks out and takes this data in these slices. And all of these points are galaxies. And so you have a ton of galaxies that we can start to do population studies on. And this is really important because you can start to build a census of what the galaxy population looks like today. And you see this large diversity of galaxies. And this is an image that I kind of showed in the intro slide to my talk. And it gives you an idea of how galaxies span from actively star forming. These galaxies have bluer colors, more gas, and are diskier. And then they start to become redder. They start to show signs of less gas and more spheroidal shapes. And if you were to extend past just the local universe, then you'd be able to go to higher redshift. And a cool thing about astronomy is that the farther you get from the Earth, the farther back you're seeing. So you're able to take images of what the galaxy looked like earlier and earlier in time in order to try and piece together a picture of how galaxies evolved from the very early universe down to the very to today's universe. And if you were to do this and try and understand the population demographics of your galaxies, you basically can take a volume of the universe, count how many blue star-forming galaxies there are, and count how many quiescent galaxies there are. And then you can plot the number density of those galaxies as a function of stellar mass to give you the stellar mass functions of these two populations at different epochs in the universe to try and understand how those populations change over time. So as you go from the earlier universe down to the later universe, you start to see that the red quiescent population here starts to dominate over the blue population, particularly at high stellar masses, giving you an indication that the quiescent fraction is growing and that it's likely that star-forming galaxies that are lower mass or that are high mass at the higher redshift universe that are actively forming stars eventually turn off their star formation and contribute to the quiescent population. So quiescent galaxies are becoming more and more numerous down to lower redshifts. So this is the question, is how do galaxies transform from being star forming to quiescent? And in order to understand that, we have to, in order to understand really the conditions under which quiescence occurs, we have to understand the conditions under which star formation occurs. So let's look at a star forming galaxy. Now, when we look at a star forming galaxy or any galaxy in general, we're only seeing a very small part of a much larger ecosystem in which the galaxy is interacting with. So the galaxy is embedded within this dark matter halo, in addition to a gaseous halo, which is shown in this kind of blue gas around the galaxy. In addition, you might have several satellite galaxies, but satellites might be interacting with the hot halo gas around galaxies in ways that would influence its star formation. And I'm really trying to understand how black holes themselves are influencing star formation. So I'm going to be only focusing on central galaxies for the rest of this talk. And so for a central galaxy, you can have this gas around your galaxy that's in the halo that's very diffuse and it's very hard to see. So that's why we only really see the very central parts. But this gas is really important because it offers the fuel that might give the galaxy fuel for star formation. And so this gas can cool, it can condense, it can fall into the center and start to form a disk of cold gas that then forms stars. And then once that process starts, the star formation gives off feedback, energetic feedback, that then interacts with the cooling from the halo in order to start to regulate the amount of cooling onto the halo based on how much star formation you have. And so this is kind of the picture I want you to have of a star-forming galaxy, a kind of self-regulated system where the star formation is regulating it. So for quiescence, this is introducing this new kind of regulation mechanism that isn't star formation. Quiescence results from the disruption of this regulation cycle, where gas cooling is now being regulated by some other process. And there's no star formation that's happening because gas is no longer cooling the galaxy. And it's important to note here that for long-term quiescence, this kind of reaccretion must be prevented in order for long-term quiescence to be a thing. So a little bit more quantitatively, if you were to look at the population of galaxies on a plot that shows a specific star formation rate, which is just the star formation rate divided by stellar mass, as a function of stellar mass, then you can see that galaxies lie on a star-forming main sequence. And then quiescent galaxies that have relatively suppressed amounts of star formation lie underneath it here. And what I want you to think about is star-forming galaxies look like this kind of regulation cycle where star formation is offering that kind of support against runaway gas cooling. And quiescent galaxies have some kind of other process that's going on that's affecting the amount of gas cooling that's going on and not having the star formation be the main regulator of that gas cooling. Okay, and the fact that there are so many quiescent galaxies makes this problem a very, very salient problem in galaxy formation evolution. How do we get all of these galaxies here to be quiescent and stop forming stars if they're all hosting this large gas halo? And this is where supermassive black holes come in. And so we think that most, if not all, galaxies host a supermassive black hole, and some of them even have supermassive black holes that have lots of gas around them that are really bright, active galactic nuclei. And if you were to zoom into one of these galaxies with an AGN, then you might see something like this, where this is at 0.1 parsec scales. This is tiny, so tiny compared to the galaxy on kiloparsec and megaparsec scales. So it's kind of incredible, because what we think is going on is that the accretion of material onto the black hole is producing all of this energy output in the form of winds, jets, and radiation pressure, etc., that then influence the growth and evolution of its host galaxy, which is kind of wild. And so one of the reasons why people think that this might be the case is because people have went out and measured black hole masses in other galaxies. This is an incredibly difficult thing to do. In order to measure a black hole mass dynamically, we need to be able to resolve this gravitational sphere of influence around the black hole. And so we can only really do that for local galaxies, where we can do that with big telescopes. And when we start looking at the gas or the stellar dynamics around these black holes, we can start to get an estimate of what their masses are. And incredibly, about 20 years ago or so, people started to realize that the black hole mass of local galaxies correlates really well with some global galaxy properties like stellar velocity dispersion and bulge mass, which again, these galaxies and black holes are operating on very, very different spatial scales and also temporal scales. The accretion of gas onto the black hole is happening quite rapidly compared to the evolution of the whole galaxy, which is happening on very long timescales. So these kind of relationships are incredible, even though they've been established for about 20 years or so. Another reason why people think black holes are important for galaxy evolution is because when we look at galaxy clusters and galaxy groups, and we take a look at their X-ray emitting halos, the hot gas that lives in the around the galaxy, surrounding the galaxy, which I talked a little bit about before, we see that there are these cavities that exist on different levels. Here's like 3 different cavities for this one group galaxy. Here's Perseus. You see the cavities here and then here, and then you even see sometimes radio emission from the jets that are launched by the black hole that fit really nicely into these cavities, showing you that the black hole might be producing this kind of phenomena that might affect the way gas cools from the halo onto the galaxy. And so this is where we come back to this picture of quiescence being this disruption of the cycle between star formation regulation of how gas cools onto your galaxy. And people have measured an estimate of the jet power and an estimate of the cooling power by looking at the cavities and the jets, and by looking at the X-ray luminosity for the cooling power, and found that they correlate, meaning that maybe the jet is really regulating the amount of cooling that can happen onto the galaxy. So this is really nice evidence. However, there's a couple of outstanding issues for the black hole paradigm that's been being built throughout these past few decades. For one, we really don't understand how energy is transferred from black hole feedback effects into the surrounding gas around the galaxy in order to actually stop the fuel, stop providing fuel for star formation in the galaxy. And so we're really not sure how this works. In addition, there's a lot of different kinds of black hole feedback. This is just one kind, this jet mode. There's also outflows that you see at smaller scales that might be affecting the availability of cold gas in the galaxies. And we're not sure how all of these different modes work together to then shape galaxy evolution. And all of these images that I showed you of the CGM, the circumgalactic medium around the galaxies being affected by black hole feedback, are all really they're all really at very massive galaxies. So the radial lobes and X-ray cavities that we see are all in a very special mass region where we can actually observe the X-ray gas because there's enough of it to emit so that our X-ray telescopes can detect the light. But you can see that there's a ton of galaxies here. They're all quiescent, and we really can't get an estimate of what their halos look like. There's some valiant efforts out there by stacking COS halos data for measuring line of sight. So we can see what the gas is at a line of sight around the galaxies. But we can't get an overall understanding of what all of that gas looks like. So this is a really, really hard problem. And so the question still remains as to whether black holes are the underlying mechanism behind quiescence, and then if so, how does it work? So the way that people have at least answered the second part of that question into pushing towards lower stellar mass regimes is by looking at the black hole galaxy correlations that I showed before. So again, these are for a smaller sample of galaxies where we can actually measure black hole masses. And in order to expand the sample of galaxies that we have, they've connected, they've linked these black hole galaxy correlations to broader galaxy quiescence correlations. So if you take the quiescent fraction of galaxies, you can see that as your stellar velocity dispersion or bulge mass grows larger, your quiescent fraction goes up. And since your stellar velocity dispersion and bulge mass grow and correlate with your black hole mass, this forms an indirect link between your black hole mass and quiescence. And so this is an indirect link, but in the next part of my talk, I'm going to be talking about how I worked on establishing a direct link between black hole mass and quiescence in galaxies. So to do this, I assembled a sample of 91 galaxies. These galaxies were chosen based on two criteria. One is that they had to have dynamical black hole mass measurements, like I said before. And what that does, so I'm plotting the black hole mass as a function of stellar mass. And what that does is it means that the X and Y axis are completely independently measured, which is really important for this study. And then my second criteria is that they have to be centrals. So I just made sure that they were the brightest galaxy around about a megaparsec from where they were. And as you can see here, once I get these two axes to be measured independently, you can see that there is a positive correlation, but there's quite a bit of scatter in the relationship between stellar mass and black hole mass. And if I color these points based on whether they lie on the star-forming main sequence here, or off the star-forming main sequence in blue and red, then what I see is a clear correlation between black hole mass and quiescence, where galaxies that host more massive black holes are more likely to be quiescent than galaxies at lower black hole masses at the same stellar mass. And this is telling us that there's a physical origin to the scatter in the black hole mass stellar mass relation. And so in other words, if you were to take two galaxies at the same stellar mass, and one of them had a more massive black hole, it could look as different as these two galaxies. And so there's really this physical origin to the scatter, and that we kind of want to understand why this is the case physically, right? What physics actually accounts for this empirical relation. But again, this is an empirical relationship. So in order to get a better handle on like what physics is happening and how physics creates this kind of relation, we need to be looking at simulations that give us kind of a way to interpret this empirical data. So can simulations form this kind of empirical relationship in their simulations? So I do that here. So here are the observations that I showed before. And then here are 4 different galaxy formation models that I analyzed in order to see whether the black hole mass stellar mass relations look similar or different from the observations. And the first thing you might notice is that none of the simulations look similarly to one another, other than they're all positively correlated, but their normalizations, their slopes, and their scatters are very different from one another. And they're also very different from the observations themselves. And so that's important. And it tells us that black hole feedback models and black hole growth models are not the same across simulations, and that is very unconstrained. But I'm going to be focusing on the qualitative result that I found in the observations, where we see this kind of separation, this clear separation between quiescent galaxies that lie at more massive black holes and star-forming galaxies that lie at lower mass black holes. Okay, and we're going to be comparing each of the simulations and trying to ask, do they agree or do they not, and why is that the case? So let's start with Galaxy S. It's a semi-analytic model that uses a halo mass threshold to produce quiescence. And so as soon as you pass a certain halo mass, galaxies become quiescent at more massive halos. And what this produces is an overlap between quiescent and star-forming galaxies on this relationship, which is in contrast to what we see in observations. And because this model doesn't take into account black hole feedback as the main producer of quiescence, that's why it doesn't agree with this data and doesn't correlate with black hole mass. And so that doesn't work. So Eagle does something interesting. It does use black hole feedback to cause quiescence. So you can have a star-forming galaxy that star-forming galaxy has a lot of gas that might be accreting onto your black hole. And for Eagle, Eagle has a lot of energy be released when there's a high black hole accretion rate event. So when the black hole is accreting at a high rate, there's a lot of energy that pushes the gas out of the galaxy. But once that gas is out of the galaxy, then the black hole is no longer accreting, and so the feedback's no longer acting. So the energy is no longer coupled, and the gas can cool right back in and produce a star-forming galaxy. So here you see at higher black hole masses, you do have quiescent galaxies, but then you also have a lot of star-forming galaxies, and that's not what we see in the observations. And so this kind of short bursty feedback doesn't seem to work to reproduce the observations. For illustrious, this one's an interesting case. You have a black hole bubble model where the black hole feedback, when it's turned on in the radio mode, they expand these bubbles into the CGM of the galaxy, into the atmospheres of the galaxy, and it completely basically removes most, if not all, of the halo gas. And it produces too low of predictions for cluster galaxies where we know they have gas around them. So in illustrious, there's almost no gas around the galaxies. We know this isn't doing the right thing, right? But what it does give us is it gives us a nice separation between quiescent and star-forming galaxies on this plane that more or less reproduces the qualitative observational results. So it does the right thing, but for the wrong reason. And then for L galaxies, it is another semi-analytic model like GAL-ICS. These two were hydrodynamical models. And for L galaxies, once your black hole energy exceeds your cooling from your halo, the galaxy turns off its star formation, and it can no longer form stars. And so the commonality between these two simulations is that once black hole feedback turns on to shut off star formation, the star formation can no longer continue because the halo gas no longer can accrete back onto the galaxy. And this kind of effective, long-lived black hole feedback seems to be the only two cases in which this kind of observational result can be produced. Does that make sense? Any questions so far? Cool. So this shows you that this kind of observational data can be really nice and a nice constraining data set for our simulations and our the physics that we might implement in our simulations for black hole feedback. So another thing about the observations that I wanted to touch on is that the boundary between quiescent and star-forming galaxies is actually sloped. And this slope has a slope of about 1, which corresponds to a line of constant black hole mass-stellar mass ratio. And it also tells you that as you get to more massive galaxies, you need a more massive black hole to show quiescence in your galaxy, which is interesting because then that might tell you that perhaps you need more feedback to turn off that star formation. So another thing is that, I was separating galaxies into blue or red for star forming or quiescent, but I actually have their star formation rates as well. And so I can actually plot in color what their specific star formation rates look like. And what I find is that their specific star formation rates decrease perpendicular to these lines of constant black hole mass-stellar mass ratio. And another way of kind of seeing that is by plotting the specific star formation rate as a function of this ratio. And you see that there's somewhat of a relationship here where there's a gradual decrease in the specific star formation rate as a function of this ratio. Again, none of the models can reproduce this data. And so this is an interesting way, perhaps we can constrain our models of black hole feedback in galaxies. Okay, so that part of my talk was all about population statistics, how we can use galaxy scaling relations and many galaxies and their global properties to understand as much as we can about how black holes interact with their host galaxies. For my next part of the talk, I'm going to be talking a little bit more specifically about how black hole feedback affects the gas around galaxies and how that might be tested between simulations and observations. So to do this, I think it's important to look at how observations and simulations are different. So in observations, we're looking at light. Light gives us information about the radiative processes that are happening in the galaxies that we're looking at. And these radiative processes are tied to different physical processes that are happening in these galaxies, which you can see here as you go into different wavelengths. And the way that this is translated into physical quantities that simulations produce is something that's very important, right? And usually what people do is take the observations, they translate them into physics, and then the simulators take those physical interpretations and compare them with their physical simulation models, the output, which is all physics. And in this project, what I'm doing is I'm taking the simulation data and I'm translating it into observations to understand whether they can replicate what the observations say rather than the other way around. So I'm going to be specifically looking at the H-alpha line emission. And just to give a little overview of what that looks like is if you take the light from a galaxy and you split it into the energy that it's emitting from that light, then you can get a spectra, which gives you a brightness as a function of the observed wavelength or energy of that light. And I'm looking specifically at the H-alpha line here, which is quite a booming line in this spectra. And what's different about line emission compared to photometry, for example, the R band, you get this large kind of region here, and you add up all the light here, and you get an image like this. Whereas in H-alpha, you're looking at a specific process that produces the H-alpha line, which is a Balmer series transition. This generally happens within star-forming regions. And so you can see, for example, here in this galaxy, the H-alpha emission is happening in this bar region, where there's patches of star formation happening all along this bar. But H-alpha is also really useful for tracing black hole feedback and its effects. And so here is an example of that. So in the way that they trace this is by looking at the line emission and whether the lines can be fit not only with a narrow component, which traces the star formation, but also a broad component, which you can see in the red here. And that broad component is produced by various different clouds traveling at kinematically decoupled speeds compared to the star formation that's in a rotating disk galaxy. And so if you can kinematically model the line emission from these two decoupled components, then you can start to get a handle on what the outflow looks like. What is the outflow? How can we characterize the outflow? And so if you look on the outskirts of the galaxy where C is, there's only narrow line, the narrow component, whereas in the center, in A, you get this broad component too, which gives you an indication that this is maybe a black hole feedback driven process that's producing this H-alpha outflow. Same here, you have this broad component here in orange, which is shown in the contours, which is more in the center, compared to the colors, which are the narrow line component. Okay, so the idea for this project is to see whether a simulated galaxy, if you were to simulate the H-alpha emission, would give you similar kinds of signatures and how we can learn from that. So there's several ways you can use this data once you do this. For example, if you have very simple kind of models, for example, biconical outflow models that observers use to try and understand their observations, you can do the same thing with your synthetic observations of the simulated galaxy and ask how well it can reproduce what the simulation tells you is going on in your galaxy. And then you can start to test your observational techniques. In addition, you can start to constrain your models. You can have different black hole feedback models and ask, okay, what is a synthetic emission that you would predict from different kinds of models with different velocities or outflow temperatures, etc. And you can start to constrain your models and what kind of models you need to use in your simulations to replicate observations. And so here I'm using the FIRE simulations. In order to do this, I place a black hole in the center of one of these FIRE galaxies at redshift 2. This galaxy was chosen at this specific time because there's a starburst going on due to this merger that's throwing in gas into the galaxy, causing it to be this starburst and supposedly feeding the black hole with a lot of gas and then enabling this kind of feedback effect. So this is what the simulation looks like. The black hole feedback model is described in Torrey et al. 2020. Basically, it's a piston of newly spawned particles around a unit sphere. It's isotropic in the way that it spawns these particles periodically. You can kind of see it's like a little piston going off. It's sped up at the last 20 million years or so. The wind is allowed to go for about 35 million years. And the idea is to see whether these winds can replicate some of the H-alpha emission that we see in observations. And by the end of the simulation, you can see that there's very little gas in the galaxy. And you could also tell that the winds were coming out at the north and south ends, but this isn't something that was put into the model, right? It just came out because of its leaving at the regions of least resistance. Okay, so the global properties of these galaxies, of this galaxy. So we have a simulation run with black hole winds and then one run without black hole winds. So you can look at the stellar mass evolution, the star formation rate evolution, and also the circular velocity within 1 kiloparsec and that evolution as a function of time since the wind started. And it's only 35 million years, so it's a very short amount of time. And what you can see is that the star formation rate goes down. So that means the stellar buildup is not as much in the simulation with black hole winds. And if the stellar buildup in the center is not as much, then the gravitational potential doesn't sink deeper. And so the circular velocity doesn't go up as much as if the starbursts were allowed to happen unhindered by black hole winds. Okay, so I really should have an image here. I need to create one. But let me paint this picture in your head about how the radiative transfer modeling happens. So I use a code called COLT, which was developed by Aaron Smith, and this was done in collaboration with him. And basically what happens, I want you to imagine a galaxy simulation. There are star particles in this galaxy simulation. There are also gas particles in your simulation. The star particles are sending out photon packets from using COLT. So COLT sends out photon packets from the star particles, which interact with the gas particles in order to adjust their ionization states. And so that ionization state is really important because then it tells you these H-alpha luminosity, the H-alpha luminosity that should be coming from those gas particles, because we're tracing gas, warm ionized gas with H-alpha. And so those gas particles are then allowed to emit in H-alpha and interact with dust and gas in the galaxy that you assume is there, and then you can produce synthetic observations by tracing how light interacts with matter in these simulations. And so these are the kind of images that we're getting. So here's the case with black hole winds off and the case with black hole winds on. And as you progress through the simulation with black hole winds on, you can see that this, again, is undergoing this very messy starburst, merger-driven evolution at this point in time. And so you can see you get a face-on kind of view of the spiral arms here. It's looking pretty clumpy, but then by the end you start to see like a dust lane here and here. So it's changing orientation because gas is being fed into the system. So it's quite messy. And then when you turn your black hole winds on, you start to see these effects of the winds kind of breaking off pieces of the H-alpha emission and depleting the amount of H-alpha you get. And you can also make velocity maps of these galaxies as well with this data that tell you the rotation or the outflow velocities from black hole winds, right? However, or hopefully, right? So if those two, so the flux and also the velocity can be summarized in this in these plots where I'm showing you the H-alpha intrinsic flux. So this isn't trying to assume an observation or telescope or convolving it with any kind of Gaussian or anything like that. This is just looking at the intrinsic flux coming from the galaxy of H-alpha, just to see what it looks like. Where is this gas coming from? And you can see that as the simulation progresses, the H-alpha luminosity and also the width in the simulation with black hole winds starts to deplete by the end of the black hole wind simulation, which is something that does not reproduce the observations, right? We expect there to be a broader profile that exceeds 1,000 kilometers per second based on these 30,000 kilometer speed winds that we're inputting into the simulation. And so the reason why this happens is because simulations have had a really hard time creating fast-moving, cooler outflows. And usually what happens, here's a cold cloud. It's interacting with a hot wind, and we're in the frame of reference of the cold cloud. And what happens is that the hot wind turns all of the cool cloud into hot winds that do not emit an H alpha. And this is generally how people have modeled winds from black holes, is this kind of cloud destruction. However, recent simulations, this was from 2018, but there's been a lot more work on this recently as well, show that there is some region of parameter space where where this cold cloud interacting with a hot wind, there produces this mixing layer, where that mixing layer can cool faster than the cloud can be destroyed by turbulent mixing. And this means that clouds can not only be accelerated by the hot wind, but they can cool and form more cool gas to then create these outflowing signatures of perhaps H alpha emission. And so my future work is going to be looking at how we can be simulating this in simulations like fire in order to get better H alpha properties that can actually be compared to the observations. At the moment, fire does not resolve these kind of processes. Okay, so getting to the end of my talk, I hope that you all come away thinking about black hole feedback as being super essential for galaxy evolution. However, the physics implemented in galaxy formation models is largely unconstrained, as I showed you in the earlier parts of my talk. And I've approached this problem in two different ways. So one, the galaxy population demographics, I've looked at them and shown how black hole mass seems to be an important predictor of quiescence, which gives us some kind of indication of the importance of black hole feedback, perhaps, in affecting the star formation in these galaxies. And then also, I've been translating simulations to be in conversation with observations in order to help interpret observations and also constrain black hole feedback models. And I've shown that outflow signatures in H alpha light are not easily captured in simulations, and more work needs to be done to be able to compare outflows, multi-phase outflows in simulations to the observations that we see. So thanks. I'll take any questions.
Thanks, Bryan. It was a great talk. Questions from, yeah.
I have a question about the simulation with black hole.
Yes.
How do you determine the strength of black hole?
Yeah. Sure. Yeah. So the question was, how do I determine the velocity, the properties of the winds in the simulation where this simulation work, where I include black hole winds? And the answer is, again, black hole feedback models are super unconstrained. We don't really know how to constrain that kind of physics. And so the idea would be to put different velocities of winds or temperatures of winds or opening angles of winds in order to determine what's the best strategy. So the 30,000 kilometers per second was a velocity chosen to replicate broad absorption line winds, but it might not be appropriate for a lower redshift case for a kind of normal Seyfert galaxy compared to a broad absorption line quasar, right? So
Got a question in the Zoom. Do your models of black hole feedback include stellar feedback from winds and supernovae? And how long does it take to quench star formation in a disk once the infall from the halo is halted?
okay, so the first question was,
Do your models of black hole feedback include stellar feedback?
okay. Do the models of black hole feedback include stellar feedback in the simulations? For all of the simulations here that I compared in the first part of my talk and also in the fire simulations, they all include stellar feedback. And they're all unique to their own simulations, but yes, they include it. And then the second question was?
How long does it take to quench star formation in a disk once the infall from the halo is halted?
That's a great question. And it's something that I've noticed it's not very long, but I haven't quantified it. But it happens pretty quickly, especially for example in illustrious TNG, where there's a kinetic wind model that tosses all that gas out. And so it's pretty immediate once the black hole wind turns on and has enough energy to then remove the gas based on the binding energy argument. So basically the gas needs to be unbound from the galaxy. And so once the black hole wind accumulates enough energy to unbind that gas, it's pretty immediate.
Yeah, for this product here, what's the prospects of expanding the number of black hole mass becoming
Yeah, this is a really hard question. People are working on this to understand the biases. I think one important approach is understanding the biases. How are our black holes chosen to be measured? And how can we understand the galaxies that we're not measuring their black holes for? Are we missing any parts of parameter space? So there's a program by Jonelle Walsh. I know that she's trying to understand how we can get a more representative sample of black hole masses. And so this kind of work is going to be key. For pushing to higher redshifts, I think that's going to be really hard, and I'm not really sure the answer to that. But at low redshifts, at least we can start to do good work for dynamical mass estimates, at least. Mm-hmm.
What process are known as the black hole feedback? I mean, like you said, the star formation quenched relatively quickly after the onset of the black hole feedback, but black hole, supermassive black hole should be there.
Right. So, okay. So when a black hole is accreting, So I guess the question was, what kind of processes are important for producing quiescence in black holes? Because black holes are always in the centers of galaxies. And so why do some galaxies show signs of being quiescent while others don't? This is a big question. I mean, so when we see galaxies that are hosting these massive outflows, the question is, we're only getting a very small, we're getting a snapshot of a larger, longer history. And we're not really sure how that energy injection into the atmospheres of galaxies is actually influencing that galaxy's evolution on long-term scales. Now, when we see these kind of jets being expanded into the atmospheres of galaxies, then we can kind of sense that, okay, well, it's happening on such large scales that this must have been happening for a long period of time. But for the outflows that I'm trying to replicate here, we're not really sure how long these effects are taking, we're not really sure how the effects are influencing the long-term star formation in galaxies. And so one reason why I want to be able to model H-alpha outflows or any kind of outflows is to then, once we get a good enough model that replicates the observations, put it into a simulation, see what it does. Does it actually halt star formation? Does it toss metals into the atmosphere, then affecting the cooling of the halo onto the galaxy? And maybe by implementing these winds in these galaxies, you're affecting the galaxy's growth, but in different ways, not by just removing all the mass, all the gas mass, you know. So it's a really hard question to answer for sure.
What do you think are the most important improvements in relation to the observations?
So I'm trying to do that work by better matching these kind of smaller scale gas properties of outflows. I think that's a really important thing, because once we get a better understanding of the multi-phase effects of black hole feedback and what models can reproduce those effects, I think that's what's going to be the key to actually understanding how black hole feedback is affecting galaxies and then constraining our models further. But that's also going to take some work on the population studies side on the larger scales, and then also, of course, on the very small scales at the accretion disk level. We're going to have to combine the efforts from the very small to the very large scales and work all together. And that's going to be a very hard problem, but worthwhile, I think.
The question was, what are the most important?
Oh, yes. Sorry.
You're good. I always forget to do it too. The question was, what are the most important improvements to models of galaxy formation?
Yes.
Are there other questions? Graduate students, I'm looking at you.
So the question was, are our models oversimplifying things? Do we need to implement completely new ways of treating black hole feedback, or can we work off of what we have? I think that, of course, the work that we've done is really important. I've only highlighted the problems, but of course they've reproduced the larger scale observational trends in the stellar mass function, et cetera. So we have a better idea of how black hole feedback should be working to limit star formation in massive galaxies, but we're not sure of the details. And I've shown that in my studies, the details aren't matching up with the observations that we have. And so I think that we can work off of what we have. We're always going to be simpler than the actual universe is, right? We're always going to have to simplify, but the idea is not to be reductive about it and to take the complexities that we know at the smaller scales and understand how we can maybe capture them in their emergent phenomenon in their emergent behavior as we try and incorporate them into galaxy formation models.
Okay, I have two questions.
Sure.
One, are your synthetic observations going to be able to give observations, better constraints on the mass loading factors? And the second question is, are there other observations that would be helpful, like say molecular gas or some other outflow phase that would be that would help constrain the models?
Also, your laptop is about to die.
Oh, okay. That's okay. Well, it's at the end of the talk. So, so Zoom heard that, right? Yeah, because of the mic. Okay. So yes, so other gas phases, of course, are important. So I'm only looking at H alpha light here in this study, but the hope is to extend this to other lines, optical and otherwise. CO would be great. People look at molecular gas outflows all the time as a result of black hole feedback. And so yes, getting a better sense of what the multi-phase gas is doing is going to be really important. And the thing is that in simulations, we have all the information for all the gas phases if we can resolve them, if we can model them. And to be able to take maybe H alpha light, for example, and see whether we can predict what the cold gas should be doing. If we know the H alpha light, that might be able to predict what kind of observations we could make in the future. So yeah, and also in terms of mass outflow rates, I think that we assume some things when we try and get mass outflow rates, for example, the density of the gas that's outflowing, and that's a key factor, right? We have to assume either a constant density or a density that changes as you go farther from the galaxy center. And we can test these assumptions in simulations and use the same kind of methods to measure mass outflow rates from the synthetic observations, and then compare that to the actual simulation and whether it's replicating the outflow properties in the physics that we have from the simulation.
Accretion series solution in the AGA solution scale, or are we at the point now where it's enough to, as you say, the velocity of the wind by hand and look at what it does?
Yeah, the question is, are we able to constrain the smaller scale accretion disk processes and I guess like, because I'm talking about changing, the black hole model in terms of the velocity of the wind or the temperature of the wind or the outflow angle, opening angle of the wind. But are we going to be able to constrain smaller scale processes? I think that we have to work from the small scales upwards and then also from the bigger scales downwards so that we can meet in the middle. So accretion disk simulations and understanding how energy is being released from the very small scales is really important to then match up to the larger scale physics that I'm trying to capture in these models. And so then we can try and understand whether we need to stochastically vary the release of energy in the larger scales and whether that would replicate the behavior that we see in the release of energy from the smaller scale accretion physics, or whether we need to do some more sophisticated kind of modeling there. That's not just stochastic, but correlates with other properties of the galaxy or other properties of smaller scale physics that we need to model. And so there's always ways to be more sophisticated and match these kind of scales.
Any other questions? Everything's crystal clear. Great. Let's give Bryan one more round of applause.
Thank you. Thanks, everyone.